Alright, so welcome everybody. So I'm going to continue the discussion from last time, which was about the connection between solid-state physics and singular learning theory. I want to be clear that it's not like a precise correspondence, right? It's more like, in the vein of much of the application of mathematics, these two things apparently different can be described using similar mathematics, and therefore the intuitions that we have in solid-state physics, and particularly the approximations that we find useful, might also inform a deeper understanding of singular learning theory. So maybe I'll just put up a brief recollection from last time. So solid-state physics 2. So last time we had the dispersion relation. So remember, that was the function that computes the energy from the wave number, which parameterizes an electron state for us. It's not the only valid quantum numbers for an electron, but usually we incorporate the other things just by having multiple energy functions. I'll talk about that a bit later. So we talked about dispersion relations, the density of states. So remember, this is the number of new states per unit volume made available when you increase the energy from E to delta E. So that's a DOS. We talked about the Fermi energy and Fermi level. So the idea there was that all the states below the Fermi level occupied Fermi surface. So you can imagine that there's some states, you organize them by energy, and then below a given energy, well, some of the states are there, and then at the Fermi level, you're looking at a level set of the energy that has some topology, geometry, and the geometry of that level set is what determines whether how the density of states behaves. So the density of states has divergences, for example, where that level set changes its topology. Well, that's one way in which it will have a divergence, not the only one. Okay, and we talked about band gaps in semiconductors, and the point of that was to illustrate the process of model making. So using these ingredients and some simple mathematics, how you can attempt to describe something like a semiconductor and have a sort of reasonable sort of first take on a theory of the physics there. And there was a kind of general paradigm which I was advertising, which was the ability to go from microstates, and you could say they're symmetries. That's unobservable, right, by definition, essentially. Well, maybe not by definition, but we sort of make up the microstates, right? We're starting from the macroscopic world in our measurements, and then we're sort of coming up with some notion of microstate. We typically can't observe those microstates directly, but the, say, symmetries of the microstates, that's the dominating factor in solid-state physics and crystals. It's the symmetry group of the crystal lattice. That determines the kind of wave functions for electrons that can exist in that medium, and through that determines the density of states. The density of states is again a sort of mathematical object. We can't observe it directly, but we can observe bulk electrical properties, like whether a material is a semiconductor. one thing I want to note in passing is that it's, well, not note in passing, it's actually the main purpose of this talk. It's the singularities in the dispersion relation which create divergences in the density of states that lead to the most observable properties of the bulk. Right? So far from being these measure zero things that are just irrelevant because they occupy such a tiny fraction of the space of momenta, or in SLT, the space of parameters, the singularities determine the most important factors of the bulk electrical properties. Now, not everything. You can, I don't want to overstate the role of singularities in solid-state physics or elsewhere, but that is the case. Okay, so last time we also discussed in twisted bilayer graphene how singularities in the dispersion relation, as I was just explaining, manifest themselves as interesting macroscopic physics. There's a whole literature on how the precise nature of the divergences and the singularities contributes to the various observed kind of phases of twisted bilayer graphene at the magic angle. So that's kind of its own thing. So I won't say much more about that. But what I'm going to treat in detail today is exactly those divergences in the density of states for carbon nanotubes. So we'll go through that in some detail, and you'll see all of this this kind of paradigm worked out in that example. But before I get to carbon nanotubes, what I want to do is spend some time on the analogies and disanalogies to SLT. I sort of gave myself some leeway last time and not sort of stopping every 5 minutes to point out the ways in which it was different from solid-state physics, but now I want to caveat a lot of these things. Okay, so I did point out that the dispersion relation, the core of the connection between solid-state physics and SLT, is that the dispersion relation, that is the energy, and the KL divergence is also appropriately thought of as an energy in SLT. So E of K and K of W, K being the KL divergence, W a parameter in SLT. Well, they're similar in that they're both reasonably thought of as an energy, and they're also similar in the sense that singularities in both determine the density of states. Or rather, divergences in the density of states. And hence, many electrical properties rest below behavior. I'm using this in the sense Watanabe does. I mean, the kind of Bayesian things, not the precise trajectories or nature of trajectories of SGD or anything. So asymptotic free energy, generalization error, and so on. So we understand in both cases how this works. I won't say any more about it. So that's an important, valid analogy between the two. Well, maybe I'll skip this one. Maybe can come back at the end. Yeah. Maybe I'm at risk of belaboring this point. Okay, I'll just mention that you can make twisted bilayer graphene with a pencil and Scotch tape. I mean, you won't be testing whether it's a superconductor without a lab, but making it is easy. Okay, so the point of saying this is that you might get the impression twisted bilayer graphene, this super exotic material, it exists only at 4 labs on Earth, and you need to be doing some insane synthesis procedure to make it. And in those kinds of weird materials, yeah, maybe singularities really matter. But that is absolutely not the case, right? TBG is easy to make, and, well, so are carbon nanotubes and many other materials in which this paradigm of divergences in the density of states determining observable and important macroscopic bulk properties like electrical properties or optical properties, this is just bog standard. This is normal, it's everywhere. And of course it's also true in statistical learning theory, as we understand. So there's nothing exotic about singularities, right? They're all around you all the time, making a difference to very ordinary physics. Okay, but I want to kind of share a note of caution here. Okay, but so we've been talking about electrical properties, like whether a material is an insulator or a conductor. Obviously that's about electrons, right? And there are no electrons in SLT. Or more to the point, no fermions in SLT. In sort of the physics language, what we're talking about in SLT is just completely bosonic. We're just talking about functions. There are no differential forms, at least in the theory as currently formulated. You can actually formulate a kind of reasonable theory, which is a generalization of SLT that takes into account the noise, the stochasticity in a way that is making use of ideas from supersymmetry, and that probably is interesting and important. So maybe you can put fermions into SLT. It's not there right now, and that's actually sort of beside the point. It's not. The point isn't to look at solid state physics and to say, there's energy levels, and I mean, you fill up to the Fermi level. Why do you fill up? Well, because they're fermions, so they can't occupy the same state, so they fill up. And all of that might look like it sort of hinges very tightly on the nature of fermions. And, well, last time we were talking about Fermi-Dirac statistics and the distribution and so on. So there is a lot in solid state physics that you can't just naively transplant to be about SLT for this reason, right? At least when you're talking about electrical properties of solids. But for example, there are other properties of solids you can talk about in solid state physics. You can talk about phonons. You can talk about sort of other things that aren't about the fermionic degrees of freedom. Those you might find an easier time translating to SLT, etc., etc. So you have to be a bit careful about what intuition you draw from solid state physics. But I'm asserting, as someone who thinks they understand both, that this isn't an obstacle to drawing some rather deep insights from one to the other, necessarily. I'll just mention, we saw last time actually a case where the Fermi-Dirac distribution became the Boltzmann distribution in some limit, right, with this calculation we did at the end of last seminar. So if you're far away from the band gap, then you can treat the Fermi-Dirac distribution of the free electrons as being basically a Boltzmann distribution, and then we're literally in the same territory as what we're talking about in SLT. But that's not, it's not always a good approximation. Okay, so that's kind of a note of caution. A second note of caution is that the analog of bands is subtle. Okay, so the electrons in a crystal are arranged in energy bands, and whether a material is a conductor or semiconductor or insulator depends on the gaps between these bands and how filled they are. That story is actually more complicated than it looks in Kittel, as recent research has shown, but that's kind of the basic story. And the response of a material to applied electric fields depends on the band structure. Right? So the theory is, at least the electrical part of the theory, is organized around bands and so on. Okay, so you could ask the question, are there bands in SLT? And if you just ask the question in the most literal way, the answer has to be no. Again, this is to do with there are no fermions in SLT, and if we're talking about bands literally as it's formulated in Kittel, then no, there are no bands in SLT. But, I mean, if you ask, okay, this conceptual object that we call bands and the role that it plays in predicting electrical properties and other properties of the material, is there something equivalent to that which plays essentially the same role or a similar role to the way bands appear in the treatment of electrical properties and materials? The answer to that is probably yes. Right? It just doesn't. It's not justified in exactly the same way as bands are. So maybe the answer is yes. It depends how you mean the question. Okay, so let me elaborate a little bit. So I didn't really say what a band was last time. So strictly speaking, a band is a branch of the dispersion relation. I've been writing capital E. Now that might seem a bit strange. When we talked about the free electron, this was just a function, right? I give you the momenta in the 3 coordinate directions, you get the energy. But how should I say this? So if you think about the wave functions propagating in a regular material like a crystal, some of them behave like plane waves, and those are the ones that basically are like free electrons, and the energy formula we had last time is correct. But those whose momenta kind of match up with the lattice, the solutions, there are no solutions to the Schrödinger equation, which are plane waves that have those momenta. The solutions near those momenta are different, and that's what's interesting about crystals, and that's where representation theory enters into solid-state physics. And depending on the kind of wave function that you take, so the wave functions that do involve momenta like that, you can write them as linear combinations of different kinds of wave functions that transform into different representations. And those have different formulas for their energy function. So you will have, for each given momenta, you will have multiple different kinds of wave functions that might have that momenta, and they each have a different formula for their energy. And those will give you different branches of the dispersion relation. And you can graph those, and they'll make surfaces that usually don't touch. Sometimes they do. And so that's the band structure. Right? So that's where bands come from. Okay. So the first distinction to SLT is that whole story was about momenta, right? So this is about, this is in a momentum space picture, whereas SLT is usually formulated in what a physicist would call position space. Now, if you've dug into the guts of SLT a bit, if you look at Spencer's thesis, for example, or elsewhere, you're often Taylor series expanding the log density ratio in some preferred basis of functions, and so maybe you don't usually take a basis that looks like plane waves, but you could introduce a kind of momentum space picture into SLT if you wanted. So far it doesn't seem to have been useful. But it's maybe not playing such an important role now. And okay, another difference is that in SSP, in solid state physics, the material is infinite and periodic. In SLT, there's no similar structure on the space of parameters, right? So the phenomena I was just discussing in momentum space for solid state physics comes from some kind of periodic irregularity in real space, position space, but we don't have some kind of structure on the space of parameters that's analogous to that in SLT. So we're not going to get crystals or anything like crystals, or at least I don't see any way of doing that. All right, so that kind of prevents a naive translation of bands into SLT. Okay, but so nevertheless, so being able to do physics is about, in some large part, having many different ways of kind of viewing your theory, right? Is the crystal the fundamental thing, or is the density of states the fundamental thing? Well, you get to change your mind about that. From the crystal point of view, what we were just discussing seems crucial to the description of the electrical property of solids. But if you can derive what you need from the density of states, then, okay, one way of getting a density of states with those particular degeneracies is to have some kind of symmetry which reflects itself in the wave functions, and therefore in the bands, and therefore in the dispersion relation, and therefore in the density of states. But if you give me some other way of getting those degeneracies in the density of states, maybe I'm just as happy to say the same kinds of things, right? So one way in which this could be the case in SLT is in models with sufficiently many phases. And we've discussed phases in this seminar. I won't go into it now. I mean phases of the Bayesian posterior. So I'm not saying phases and bands are the same thing. That's not, I mean, especially in solid state physics, they're related, but they're not like the same thing. That's not a dictionary I'm setting up here. But if you have many phases of the Bayesian posterior, which create dense enough intervals of free energies, some of the same intuitions around bands may apply. This has got a big question mark on it, right? But it's not crazy. Okay. Let's see. Yeah, maybe I'll pause here for questions. So I'm going to move on to talking about spectroscopy and carbon nanowires now. But regarding this sort of quasi-dictionary between solid-state physics and SLT, any questions? All right, seems not. Okay, let's talk about spectroscopy. This is really cool. So as a physics undergrad, I never knew whether to be appalled or delighted at how easy the math was. It's like, I thought the deep secrets of the universe were going to be really hardcore math, and maybe they are. Later you find that out, but it's amazing what you can do with very simple mathematics. So let me tell you about scanning tunneling microscopes. So in a scanning tunneling microscope. Maybe you don't care about microscopes. Too bad. No, I mean, you need to sort of understand the formula. Somebody committed suicide at that comment. Sorry to upset you. So the formula which I'm going to give you for the differential conductance, which is how you think about what a scanning tunneling microscope is doing. I want you to see that formula, understand the role of the density of states in it, and just get why actually it's completely reasonable to think about an analogous device for learning machines, right? And that's the kind of bridge that I want you to be able to walk across between these two fields, right? Okay. So in a scanning tunneling microscope, an instrument with a sharp metal tip, which is about 1 atom, is brought to within a nanometer of the conducting sample. So here's the sample, and here's the distance, z. So a voltage bias. So voltage is applied across the sample. And there's a tunneling current that flows from the sample to the wire. To the microscope. And we measure that current. All right, so that's V, and that's I. And the current is proportional to the tunneling probability. Okay, so that's the tunneling probability itself is proportional to the exponential of some stuff we don't care about. Maybe I'll say briefly what the terms in the bracket are, but what we care about is this. So phi is the effective barrier height that the electron has to tunnel across. All right, so we have this exponential dependence on the gap z. Now the result of that exponential sensitivity is that very small changes in that distance z translate to large changes in the tunneling probability and hence the observed current. So for example, a 0.1 nanometer change in z can lead to an order of magnitude change in the tunneling probability. All right. So the STM current, so as you probably know, this is how you see atomic scale objects. The STM tunneling current, I as a function of bias V, gives spatial and spectroscopic information about the quantum states. Spatial, I guess, is obvious because you can move the tip around and observe how it changes. Spectroscopic, for reasons I'll explain in a moment. And the relevant formula here is the following. So what's called the differential conductance, so that's di dv, is proportional to the tunneling probability. I'll explain what this J is in a second. The amplitude and density of states. So this will take some unpacking. giving you this jargon because if you look at some of these papers to do with twisted bilayer graphene or any of the solid state literature, you'll see this term. Because this is most of the experimental plots you'll find on the front page of a paper about, say, graphene, will have a plot of the differential conductance against the bias. That's one of the standard things you'll see. So conductance means the reciprocal of resistance, right? And you'll remember that V equals IR. So V on I is R. The reciprocal of R is I on V. That's the conductance. Differential conductance is dI on dV. All right. So on the right-hand side here we have, this is the wave function. So there's like J, we're expanding in some basis of eigenstates. We have some wave function J, some quantum number, psi J, some quantum numbers J. That state to do with J has energy epsilon J. This is to do with the bias voltage V and the charge electron E, energy, charge. This, yeah, maybe I'll underline it here. So this is the tunneling electron energy. Right, so what this formula says is that the thing you can measure, which is the differential conductance, is proportional to this tunneling probability and these other terms. You see the density of states here. This is what this term is. Density of states. Okay, so it says that if the tunneling electron energy is at, so if it's equal to one of these EJs, just think of the density of states as being just a, just suppose it's discrete, right? So it's just 1 or 0 depending on, it's just a delta function, depending on whether the tunneling electron energy is equal to EJ, epsilon J or not. So if it is, you get a contribution to the differential conductance from the amplitude of the wave function at that point. So RT is the tip of the, so this is RT. Right, so looking at that, ignoring the density of states for a moment, you can tell that this allows you to see the wave function, right, or at least the amplitude. And you can even look at individual states, right, because you just tune the tunneling electron energy by tuning the bias voltage V to be at some particular epsilon J, and then only that state will contribute, and you get to see the amplitude of that wave function, right? And indeed, you really can see it. So let me, bear with me for a second, and I'll try and get a picture up. Yep, there it is. Okay, I hope you can see that. So that's a can you see that? It may not have gone through moderation, so I hope you can. Cool. So that's what's called a quantum corral. So actually I forget. I think they're iron atoms in the corral. I believe that's right. Don't have Kittle in front of me. So, and what you're seeing in the middle is, so this is a picture of the differential conductance, I guess, scaled somehow. And what you see in the middle is one of the quantum states for the, I think it's maybe there's a copper atom in the center or something. But you're seeing the amplitude, those rings there, is a picture of one of those quantum states. All right? And if you tuned the bias voltage differently, you would see a different set of structures in there. Right? So this is pretty amazing. And that comes from this formula. All right. So that's how a scanning tunneling microscope works. I said ignore the density of states. Now stop ignoring the density of states. So you can see there that if the density of states, if this were a continuous thing, then if you were tuning V, maybe I'll go back. If you were tuning V and therefore changing the tunneling electron energy, and you tuned it past a value of the energy for which there was a divergence in the density of states, the right-hand side would blow up as V approaches that particular critical value, and therefore so would the differential conductance. So you would predict based on this formula that you should be able to see divergences in the density of states in the plots of the differential conductance. And yeah, let me show you a plot. Okay. So there on the right hand side, maybe you want to make that full screen actually, it's a bit blurred on the two-board view. So on the right hand side, I'll talk about the left hand plot in a moment. You see on the y-axis the differential conductance. It's scaled by I on V, just ignore that. That's the y-axis. The scaling actually varies on the paper. It's not always I on V. And on, if I understand it correctly, and on the x-axis you see the voltage bias. So what you're doing there is you're probing different level sets of the dispersion relation of the energy function, right? That's what happens when you vary V. You're looking at different level sets. And you can see these divergences. And they're not exactly divergences. They don't go to infinity, right? Because that's not how nature works. But really that's, I don't know if I want to say really, but our puny mathematical models make this into an infinity. Okay, and that's, you know, you've got some macroscopic quantity of material, you put a voltage across it, you hook up your machine, and there you see these beautiful divergences. And what these come from are, so these are from divergences in the density of states and from singularities in the dispersion relation. So what well, I didn't tell you what this graph is for. This graph is the differential conductance for a sample of carbon nanotubes. Right, so the next thing I want to do now is go through the derivation of the density of states for this example. It's very simple. And then sort of explain this picture. So you can see on the left-hand side, there's a plot of energy versus density. So sort of this is a graph rotated of the density of states. And you see conduction band at the top, valence band at the bottom. We talked about that last time. You see absorption and fluorescence. So this is absorption and emission of photons. This is not electrical properties. This is optical properties. So I'll explain how that also depends on the density of states. So on the right-hand side is electrical, on the left-hand side optical, and yeah, hence the term spectroscopy. Okay, any questions about these pictures before I do some math? Okay, so let's do a little bit of math. Okay, so example. Nanoscale wire. Yeah, for example, carbon nanotubes. There's nothing specific about carbon here. All right. There's kind of a little exercise in first year quantum mechanics here, which I'll skip. So the energies and eigenstates are, let me see, I have another picture of this. Maybe I'll just draw one. So it's not one-dimensional. but it's somehow like discrete in all but one direction. In a sense, I'll explain in a moment. So that's the z direction. This is x and y. I think that's right-handed, yeah. Okay, so we're going to assume that the only interesting stuff happens in the z direction. So the energies are going to be Eij, epsilon ij. I'll explain that in a second. So here I and j are quantum numbers in the x and z x and y directions. So if you wanted to solve this problem, you'd set up the x and y directions as a particle in the box with some infinite potential. Well, you would split the wave function into a product. You think about it as a tensor product of Hilbert spaces, one for the z direction, one for the xy directions. You solve the problem in the xy directions, assuming so you just get these quantized things, like a particle in a box, labeled by these two quantum numbers ij, so psi ij is some understood functions, and we're not going to care about them, times in the z direction you actually have plane wave solutions, right? E to the I kz, k is the z moment. Okay. I guess that explains this. What about this here? Well, you have some energy from the xy component of the wave function, right? And that's just the energy of this psi ij. And then you have the energy to do with the z momenta. Right. So the dispersion relation, for reasons I explained earlier, is really a family of bands. Kittel would say 1D subbands. Right? For each, you have many different wave functions with the same momenta k. Right? With a fixed momenta k, you have as many different wave functions with that momenta as you do quantum numbers I, j. And they each determine a different dispersion relation. I've written it for you. And therefore different bands. Right? Okay, so the density of states, well, if I tell you I've got an increase of energy by epsilon, how many new states do you get? Well, you get however many new states you get in each one of these kind of separate kinds of wave function, and you add them all together. And what about this particular one? Well, if you fix the quantum numbers ij, we're just talking about the energy, then we fix the energy contribution from those directions, right? And then we're just talking about a free electron gas in one dimension. And you know the formula for the density of states for a free electron gas. Right? So if you remember, the number of states in a free electron gas in dimension d was proportional to e to the d on 2, just the volume of a sphere, radius radius root e. Sorry. Yes. So therefore the density of states is the derivative, so it's d on 2 minus 1. If d is 1, for a one-dimensional free electron gas, I get e to the minus half. So d I j epsilon is just, well, there's some constants of proportionality. I don't think I care. I won't even write them. So it's proportional to stuff we don't care about. Epsilon minus epsilon ij to the minus 1/2. Okay, so you've got for epsilon greater than epsilon ij, and it's 0 for epsilon less than epsilon ij. It's got a divergence when epsilon is equal to epsilon ij. I just won't put it in there. Okay, so you see that the density of states is the sum of these functions which have divergences at these values of the energy that have to do with some bands becoming accessible. Right? So the derivative is infinite. Well, the moment that band becomes accessible, there's an instantaneous infinite change in the number of states. Right. So you might think this is kind of like a cheating way to get a singularity, and I kind of agree, but well, this is a real thing. Mathematically, it would be more interesting if there was just a sort of genuine singularity that didn't involve contributions from these partially defined functions or whatever. But well, that does also really happen. That's what's happening in twisted bilayer graphene, for instance, but it's harder to explain than this example. So, okay, so we see, and anyway, this illustrates the essential point. We get divergences when some bands become sort of newly available, and these are called Van Hove singularities. VHS. Okay. I think that's the simplest example of a Van Hove singularity I can think of anyway. So these singularities affect the electrical and optical properties of 1D systems, as I've already said. And let's go back to the picture now and look at this carbon nanotube example. So you can see on the left-hand side these kind of horizontal lines. These are the epsilon ij's. And yeah, well, it's a little bit of a lie because it's not like you're actually considering a single carbon nanotube in a sample. If you're running a voltage across it, you've actually got many carbon nanotubes in your sample. And as far as I understand it, it's the different radii and chirality of those carbon nanotubes together which contribute to make these bands that you can see here. But okay, the story is correct. The origin of this structure is to do with these Van Hove singularities. Okay. I promised to explain this absorption and fluorescence arrows. The rest should be clear. So those graphs that you, well, let's see. So this line here. So this is like this value over here is epsilon C2. C2 for second band in the conductance, second conductance band. And then this over here is the graph of epsilon minus epsilon C2 to the minus 1/2. Right. Okay, so we've been talking about electrical properties, but I kind of want to really drive home this point about spectroscopy by talking about the absorption and emission of photons briefly. So the optical, because I think it's just so cool that you can see these singularities. The optical emission and absorption of semiconducting nanotubes. Is dominated by these singularities. So I'll write the formula, but while I'm writing it, I'll give you the kind of high-level version. All right. So Maybe I'll even just let you look at the picture in OrbCam while I'm writing. So if you look at that left-hand picture there, well, we've got these divergences in the density of states. That's the organizing structure for that graph, right? Now, the density of states diverging means you get a lot of new states per unit volume. Now that means that if you're thinking about transitions between energy states, well, unless you have some reason to believe otherwise, most of the transitions will be between states that are in those places where it diverged, right? Because that just dominates the set of states. So to a first approximation, what you care about are transitions that involve those divergent energies, or rather electrons that are at those divergent energies. Now that's the kind of loose version of this formula, which is called Fermi's golden rule. This is just the polarization of the photon, and this is the momentum of the electron, and so on. I don't want to explain what's going on here really in this term in brackets. There's a general formula where the thing that goes inside here is the perturbed Hamiltonian, and this is a ground state, and so on. But anyways, there's some amplitude term there. But what I really want you to pay attention to is the density of states term. So what is this saying? It's saying that, well, it's a delta function when epsilon j, the final energy, is equal to the initial energy plus the energy of the incident photon, right, depending on its frequency, omega. Okay, so at places where there are lots of states, where the density of states is divergent, you'll get an enhanced response in terms of this. This is the transition rate, I should have said, sorry. So Fermi's golden rule tells you what the transition rate is between two states, well, in many systems, but in particular in a semiconductor like this. So where the density of states is divergent, you'll get an enhanced response. So there will be many more transitions between two states, epsilon I and epsilon j, if both are places where the density of states diverges and the gap between them. So and h omega is the gap between them. So if we go back to this picture here, so this would be an example of a h omega. Right, this you get to choose, right? That's the frequency of the light. So if you pick the light at the right frequency, some frequencies it just really won't do much with. It won't absorb them, right? But if you pick a frequency that is a gap between two of these divergences of the density of states, then the system will eat it up. It'll absorb it and then re-emit it. And the emission will also be dominated by transitions between these energy levels. All right. So the upshot there is that you can actually look at this material, and the color of the material is to do with the singular structure of the density of states, and hence the divergent structure of the density of states, and hence the singular structure of the dispersion relation. Right. So that's you could hardly get more self-evident than the color of the thing. Obviously, it's probably not in the visual spectrum, but whatever. Okay. So that's it for the physics part. I want to make some more speculative comments on what this means for SLT and research directions, but that's sort of different. So maybe if you have any questions about the physics story here, now is the time to ask. We need to find some new boards. Follow me, please. Okay, so as I said, the analogy between solid-state physics and SLT isn't perfect, but it's good enough to be useful. I'll just read out some quotes from some of the literature around Van Hove singularities and twisted bilayer graphene to give you a bit of a flavor for the statements you can now understand. The references are in the written notes. So the first one, I think this is one of the first papers due to the original group on twisted bilayer graphene. It says, if the Fermi level lies in the vicinity of a Van Hove point, the singular DOS determines the physical behavior due to the large number of available low-energy states. Right? So hopefully that sounds familiar, given what we just discussed. Second quote. This is from a very interesting paper which is applying renormalization group methods to understand some details of what's happening near the magic angle in TBG. Quote, due to the power law divergence in the density of states, the high-order saddle points are more dominant than the other parts of the Fermi surface at low energy. We thus construct the low-energy theory by approximating the Fermi surface with 6 patches in the vicinity of these points. That's the starting point of the RG process. High-order saddle points is such a gross term. They're not saddle points. It's like this reluctance to let go of the classification into minima, maxima, and saddle points. They're not saddle points. They're singularities that are more complicated than saddle points. But when you see in this literature high-order saddle point or high-order VHS, what they mean is just a singularity that's more complicated than a saddle. Okay. So let me draw a kind of 2 pyramids. So for those of you who don't sort of have some overlap with physics, I just want to explain the relationship between, there's roughly speaking like 3 parts of physics. You could say there's experimental physics. You could say there's theoretical physics. Obviously there's no hard and fast boundary between these things, but physicists will often self-identify into one of these categories. So this is, I'm talking about solid-state physics in particular. Okay, so what goes in experimental physics? Well, it's stuff like carbon nanotubes and measuring the differential conductance. It's twisted bilayer graphene and measuring whether that's a superconductor and all the kind of and all the rest of solid-state physics that's experimental. Abstracted out of those experiments is theoretical physics, and that's what we've been doing, basically, or discussing, right? That's what you'll find in Kittel in the parts that aren't presenting numbers from experiments. It's theoretical physics. And that's organized around, in this case, things like density of states, perturbations from the assumption of being a free electron, RG methods. And what I wanted to illustrate over the last 2 seminars was part of how that works, right? So it's different from proving things. It's a set of good approximations and domains in which the approximations are reasonably valid, matched to predictions in specific experiments where those approximations and the formulas that flow from them are borne out, right? And it's kind of a body of knowledge of that form. And that's all buttressed by mathematical physics, which provides the concepts that you would use to explain the theoretical physics, things like groups and topology and geometry and so on. Right, so the beginning of Kittel's book is a discussion of crystal lattices, and it doesn't really talk about group representations, but you could take a second treatment of solid-state physics that would do that. There's the topology of Fermi surfaces. Again, that wouldn't be discussed in Kittel, but if you went further, you would talk about that. And then in the modern literature, you'll find more about geometry, as we've discussed. Right, so there are papers about the classification of ADE singularities and catastrophes for experimental physicists in this literature, right? Because of this kind of in the interaction between these layers, right? So the mathematical physics, it's not always that proving things there is the essential contribution, but it's organizing the kind of, you could say, hacks that are in the theoretical layer, suggesting new ones. The proofs take you out further into the territory where you can make new approximations and then look for new physics, and that's how it all works together. Okay, obviously that's a very abbreviated take on how it works. And I want to indicate devices in this hierarchy here. We talked about the scanning tunneling microscope. So what is the role of a device like that in solid-state physics? Well, that's the device that the devices co-evolve with the physics, right? So the conceptual architecture of solid-state physics has these density of state plots in it, right? This differential conductance plot. And then you look at the peaks and you say something about the band structure. So maybe that's the only time you ever have direct evidence of the band structure in your material, is looking at that kind of plot, right? It's not like somebody hands you the band structure. You have to infer it, and you infer it from the output of these devices. So the devices are designed on the basis of the theoretical physics and interpreted on that basis, and they're how you see and organize the experiments. All right, so forgive me for giving you a history of physics lesson, but now I want to just point out that we kind of lack maybe 2 layers of this pyramid in SLT. Okay, so we have experiment, we have theory, and we have math. And part of the point of the previous board is to distinguish these 2 things a bit, right? A theoretical physicist is not the same thing as a mathematical physicist. Not always, anyway. They could be the same, there could be one person doing both at different times, and usually that is the case. But the aim in theoretical physics isn't necessarily to prove things, as in a rigorous proof, although sometimes the arguments shade into rigorous proofs. And similarly, we need something like this in SLT, right? At least if we're to apply it to deep learning or to, say, AI alignment. So if we want to do things with large-scale systems about which we'll never prove anything, right? We're not going to prove that the RLCT of a large transformer model is X. So what are we going to do then? Well, we do theoretical physics or some analog of that. So we have a bunch of principles informed by the mathematical foundations. We know regimes in which those approximations are valid, and we know systems of how to make deductions on the basis of those approximations. I mean, that's what solid-state physics is. That's what Kittle's book is. All right, so let me fill in a little bit here. So, I mean, of course, we talk about this all the time, right? We have statistics, we have geometry, we have etc. I mean, the kind of thing that would go in here is part of the theory of bands or phases and phase transitions. Right? Some of that will be rigorous as much as possible. But it won't always be appropriate for everything we do. I mean, it depends what we're aiming at, right? But if we're applying SLT, it won't always be that the goal is to prove a thing, just as it isn't in theoretical physics. So if you're not proving things, well then how do you know if it's right or not? Well, that's where the experiments come in, right? So it's my opinion that we need a body of toy models, like the carbon nanotubes in solid-state physics. They exhibit some interesting physics, but everybody can reproduce it in their lab. It's a simple system. So we need toy models, the standard replicable. In which the theoretical approximations that we're developing do work, right? They do describe some of the observed physics or learning behavior or whatever you want to call it. And the bridge between those two is, well, something we have to figure out, right? You might call it a sort of analog of a scanning tunneling microscope. So something that is sensitive to the density of states, can reveal the structure of the density of states in a way that sort of reflects other things that we're measuring in the experiments. How exactly to do that? I mean, I don't know. That's research, right? But it's there are many devices like that in solid-state physics, and not all of them will sort of have reasonable analogs, but they might inspire some ideas. All right. And another thing we should borrow from solid-state physics is the RG techniques. Right? It's just absolutely clear that many of the arguments based on renormalization group flow techniques, for example, in this paper I'm citing in the notes and that I quoted from earlier, one can just do this in SLT. You may not be able to prove that it's valid, but we should be able to find toy models in which we can do RG-based arguments and have those reveal the things we see in the experiments. Right? So that's the kind of thing, in addition to proving lots of beautiful theorems, which are still very important. But we need these other two layers because the rigorous part is it's hard and takes a lot of time and won't get us to where we need to get on its own. Okay, so I'm going to stop there. Thanks, everybody. Questions? Suggestions? Build the device. Tell me how to build it.
It's a really useful framing.
Yeah, thanks. I would say that part of what Edmund is doing right now in his research is kind of inching towards building devices like this. I don't know if you would disagree with that framing, Edmund, but I think you would recognize what you're doing in this picture, right?
I was about to say that. No, not about to say that, but that I just like, oh, yeah, that's what I'm doing.
Right.
When you say that, yeah.
Yeah, it's tempting to think. I mean, the obvious analog of conductance would be to look at kind of the movement of trajectories under, well, let's say under the gradient of k with some noise near W0, right? I mean, how fast do they move? It's not crazy to compare that to the current. But yeah, things like that. So if we simulate trajectories near singular level sets, I mean, that's not, as I said earlier, they're not electrons, right? It's not directly analogous, but all we need is a formula like that with a right-hand side that has the density of states in it, and then we're off to the races, right? So I think it's doable. I haven't, this is the first time I formulated this way in my head was like this morning. So I haven't thought about it, but I think it's doable.
Is there any in solid-state physics, the fact that colors arise from just there being so many more available states at those singular blow-ups. Sorry, not blow-ups. That means something else. But those, when the density of states diverges, there are so many more states available that it's overwhelmingly likely that you're going to transition from one to another, and therefore it's those colors that you see in the spectrum. Is there anything written in the literature, or even, I don't know, computed by Edmund, that is analogous to that, where you see in learning dynamics a jump? I guess that's a phase transition. Is it?
Yeah.
Sorry, a jump from where to where?
From one. Okay, well maybe I need to back up. In the picture with the left and the right, where the spectrum picture that Dan showed, there's a photon is emitted when an electron transitions from one state to another, and it jumps from one spike on the left-hand side of that board to another spike in that graph on the left-hand side, right?
Uh-huh.
And it jumps between those two spikes because there are so many more available sort of ways to be for electrons in the spikes, and those spikes correspond to level sets of the KL divergence.
Yeah, so the plots we're showing sometimes from section 7.6 of Watanabe's book arguably have a similar explanation, where if you kind of coarse grain, I mean, if you just line up the energy, the KL divergence from 0 at the bottom to infinity at the top, and then you look at the density of states and look where it diverges, well, those divergences would probably be singular level sets of K. Some of those, not all of them, but some of them will qualify as phases in the language we've kind of adopted, where, it would be somewhere where like a local minima of the KL divergence, blah, 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 satisfying some conditions, like somewhere where the probability mass of the posterior might concentrate, and there will be a divergence of the density of states there, and it's clear that somehow that's important, transitioning between two of those kinds of densities of states, but we lack photons. We don't, to put it differently, the Hamiltonian doesn't couple to any degrees of freedom that we can kind of just send in and read out. The only degrees of freedom we couple it to, I mean, when we do a SGD run, or we put in Markov chain Monte Carlo, where especially in Markov chain Monte Carlo, actually, because we introduce kind of these noise terms or whatever, where we're coupling the loss function, the Hamiltonian, the KL divergence, to other degrees of freedom by the position degrees of freedom of the particle, for example. And then we can read out something from that, but we don't have any interactions quite like the effective Hamiltonian for the solid state physical system has the fermionic terms in it that involve creating and destroying electron states at different points in the lattice, but it also has terms in it that come from QED, I guess, from interactions between the electrons and the photons. And those terms kind of allow you to pull little bits of energy out or put them in and see what's happening. And we don't have an obvious analog of that, at least not that I see.
I think we can imagine having a trillion particles, which is, in my mind, analogous to SGD trajectories, but a trillion of them running on the loss surface, and if you keep track of for what proportion of them stays in which region for how long and things like that, that could correspond to density of states, and the transition, we will have to have some analog of injecting energy into the system so that the trillion electrons, some of them have some transition probability going from one state to the other one. yeah, I'm just repeating what Dan said, that there's a lot of things that we don't have an analog of, and particularly so particles occupying states and ways to inject energy.
Yeah, I guess you could imagine. I mean, the dumbest thing you could do would just be to like have trajectories and then give it a big hit with some noise and see like if it ends up somewhere or other, right?
I think that's more analogous to raising temperature than injecting photons.
Yeah, but if you just give it like one crazy big step and then it returns to what it was doing, you know what I mean? So it's not like, yeah, I don't know. I mean, that's essentially what happens when there's an incident photon, right? You could think about it as, well, maybe phonons are actually a better analog. So phonons, how can I explain phonons briefly? So the crystal lattice doesn't stay exactly in its lattice positions. There's, of course, intermolecular forces between the atoms, the ions in the lattice. That has a ground state, which is where they're supposed to be, so to speak. But there are perturbations away from that ground state. There's a kind of nice mathematical story there. Those perturbations can be thought of as what are called Goldstone bosons. They're due to the symmetry of the situation. In lattices, they're called phonons. You can think of that as like the, I guess, depending on your level of physics, you think of particles as like real things. It's not always like, sometimes in the mathematics you can find a thing that behaves like a particle, but it's not, not something you can spit out at the LHC of a collision or something. So phonons are like that. They're not kind of like electrons, but they're they're kind of ways of pumping energy, modes you can pump energy into in a crystal lattice, and they travel around on the lattice. You can think about it like as the atomic, the most fundamental unit of vibrating an element of the crystal away from its lattice position. Anyway, so those travel through the lattice. They interact with the electrons, and that's a big part of solid-state physics. So I wonder if there's even a sense in which, I don't know. I mean, there's lots of noise in SLT, right? And for example, in the sampling, and you might think of, maybe there's some way of thinking of some of those perturbations in the system as being analogous to phonons. Like suppose we trained something for a while with one sample, Kn, and then we resample, and we see what happens. Right.
I was almost going to say, like, we resample, but it's sampling from a true distribution that is, well, if it is injecting energy, then we want to sampling a true distribution which is closer to the minimum. I need to work it out, but like there's so you move the true distribution closer or further away depending on whether or not you want to lower or but that's more like changing the ground state.
Yeah, I think so. Yeah, we have to keep a careful balance between, it's tempting to do the non-rigorous stuff because proofs are hard. But we need to do both, and when we're doing the non-rigorous stuff, we need to also be very systematic about it. So I think we should try all the things, because maybe there's that's how experimental physics works, right? You try an insane number of variations of the experiment and the device, and then one of them works. Actually, this is where another thing I wanted to say and didn't write down was, I mentioned toy models. I think we should pay very close attention to what the mechanistic interpretability people are doing in the sort of alignment community. So, for example, at Anthropic and also at OpenAI, they have these very interesting papers with small ReLU networks or small transformer networks. I think we should prioritize. I mean, maybe we haven't thought so much about them because it's hard for us to prove things about them. That's fine. But with regards to this second layer, the theoretical part, We should pay very close attention to those models because they have started to figure out some of the kinds of measurements that you might want to do. Right? So we should not be shy in kind of running with those ideas or and developing on the back of what they're doing. And the models they're using, first of all, they're interesting toy models. Secondly, there's an existing audience of people who care about them. So maybe that's a good place to start.